Look at almost any major mining operation in the world today, and you are looking at a process built on sodium cyanide. It is the foundational chemical for extracting most of the global gold supply. But that established baseline is running into a geological wall. The simple, easy-to-process ore veins that built this infrastructure are rapidly depleting. What operators are left pulling out of the ground is refractory gold ore. It's a complex rock type that traps the gold tightly and is much more difficult to break down. When you run refractory ore through a traditional cyanide process, the chemistry struggles, the leaching times drag out, and expensive equipment sits occupied for long periods just to process the same amount of material. That slowdown hits a mining operation's overall efficiency directly. Longer leaching cycles mean lower throughput, tying up capital and dragging down the profitability of the entire site. The industry is stuck in a structural bottleneck. The legacy chemical process operators rely on is mismatched with the complex geology they actually have to mine today. Attempting to force cyanide to work faster on these complex ores means increasing the chemical concentration, which immediately escalates the risk on site, and the baseline risk is already severe. Sodium cyanide carries an extreme acute toxicity that leaves zero margin for error in handling. It presents a dual threat. A single mishandling incident poses an immediate, fatal danger to human and animal life, while an uncontrolled spill guarantees long-term pollution to the surrounding ecological system. This creates a difficult dilemma for mining directors. They need a safer, faster extraction chemical, but they cannot walk away from the millions of dollars already sunk into their existing processing infrastructure. To solve this, we have to systematically evaluate the historical challengers and modern alternatives to see if a true drop-in replacement actually exists, one that delivers the speed and safety operators need without forcing a total system rebuild. The first category of alternatives tested by the industry relied on halogens, specifically through chlorination and bromination processes. This bar chart comparing extraction speeds shows their primary metallurgical appeal. Halogens like bromine can achieve recovery rates of 90 to 95%, working in a fraction of the time it takes traditional cyanide. But as the third column on this chart reveals, the industrial viability of the halogen process collapses at scale. The flaw is stability. Chlorination causes toxic gas volatilization when exposed to open air. Halogens offered a false victory. They simply traded a water pollution hazard for an uncontrollable air pollution hazard, failing the safety mandate. The next wave of research shifted to complex compounds, most notably thiourea and thiosulfates. These chemicals have a strong theoretical appeal because their reactions almost entirely eliminate the toxic hazards associated with cyanide. They break down the ore safely. But an isolated laboratory success rarely survives contact with the realities of a sprawling, open-air mining facility. The first operational trap of complex compounds is their exceedingly narrow operating range. Even a slight fluctuation in the composition of the raw ore disrupts the entire chemical process. This line graph tracking operational costs exposes the second, fatal trap. Maintaining that delicate reaction requires high chemical consumption rates, creating steep costs compared to the flat predictability of cyanide. Very quickly, the volume of chemical required costs more than the value of the gold extracted from the rock. Complex compounds solve the ecological problem, but they destroy the operation's profit margins in the process. They cannot be scaled. That brings us to the current generation of extraction chemistry, modern substitutes like JIN CHAN, which operate in normal temperature alkaline water. The critical differentiator of this chemical class is compatibility. Implementing it requires zero retrofitting and zero capital expenditure for new infrastructure. It acts as a true drop-in substitute. You can pour it directly into your existing CIP, heap leaching, and pool leaching production flows, exactly as you would with sodium cyanide. Metallurgically, it holds its own. The leaching rate and recovery speed match or exceed the performance of traditional cyanide, even on complex refractory ores. To maximize that yield, operators pair the substitute with activated carbon, the optimal material for the specific extraction reaction. Modern substitutes break the historical compromise. They deliver a green, non-toxic extraction method without forcing an operation to abandon their existing equipment. This comparison matrix proves which chemistry serves modern operators. Cyanide keeps costs low, but fails on toxicity and speed. Halogens provide speed, but carry pollution risks. Complex compounds guarantee safety, but introduce high costs. Modern substitutes provide safety, matched yield, and zero retrofit costs. By isolating the variables, the drop-in substitute emerges as the only chemistry that satisfies all three modern mining constraints: cost, safety, and yield. Gold miners can now choose a chemical reagent that solves ecological problems without compromising industrial performance. But before an operator commits to the switch, there is one final, strict operational reality check. This decision tree reveals the single vulnerability of modern drop-in substitutes: strict ambient temperature requirements. The decision rests on whether your local temperature stays above 10 degrees Celsius. If yes, operations in temperate or warm climates have a clear path. Swapping out cyanide provides a direct upgrade to safety and environmental profiles, with zero operational downside. If no, the economics flip. In subarctic or harsh winter climates, the immense energy required to heat millions of gallons of slurry above 10 degrees negates all chemical cost savings. For those specific cold weather operations, traditional sodium cyanide, paired with the strictest possible safety protocols, remains the unavoidable and necessary baseline. Adopting a cleaner extraction process comes down to a simple calculation: matching the chemistry to the climate of the site.